Yeah, thank you very much, everyone. I'm really sorry about all the problems, but yeah, hopefully this is going to work. Okay, thank you so much for the invitation. It's really great to be able to speak here today. So yeah, the kinds of problems that I want to talk about today are problems from the world of arithmetic geometry, and well, everything that I say today, I'm going to basically say about the J function, just because it's easy to talk about a specific situation. But this is like a much broader program. So this is something that is supposed to work in lots of circumstances for all kinds of very interesting functions that arise in arithmetic geometry and that have interesting algebraic properties, like, for example, exponential functions or the Weierstrass P function, automorphic functions, things like that. So just for the purposes of presentation, I'm trying to, I'm going to talk about today just about the J function, but like I said, it should be understood that this is supposed to work more generally. So to start with, I'm going to go a little bit over the J function and some of its basic properties. The J function arises in the study of elliptic curves, of complex elliptic curves. And so just for notational purposes, we're going to use H for the upper half plane. And then there is this function J, which goes from the upper half plane into the complex numbers, which happens to be holomorphic and surjective and transcendental. And the reason why people study this function is because what it does is that it classifies isomorphism classes of complex elliptic curves. So if you have 2 points in the upper half plane, those points will define 2 different lattices on the complex plane. And then if you take the corresponding quotients, you will get 2 elliptic curves. And those elliptic curves will be isomorphic if and only if the corresponding J values are the same. So what this J function is doing is that it's giving the complex plane a moduli structure. It's a moduli for the space of complex elliptic curves. Oh, I should also point out that this is all of this is joint work with Sebastian Herrero, who is at Pontificia Universidad Católica de Chile. Now, even though the J function is a transcendental function, it has important algebraic properties. So I want to go over these properties now, functional properties of the J function. So suppose that you have, or well, no, not suppose, but everybody I think knows that on the upper half plane, you have the action by matrices with real coefficients and positive determinant. And it acts, those matrices act on the upper half plane via these Möbius transformations. And here is the action described. Now, in some cases, for certain kinds of matrices, the J function is able to witness the action. And so in order to be able to say this precisely, what we say is that there is a family, a countable family here, phi sub n, of polynomials with integer coefficients called the family of modular polynomials. And the property that these modular polynomials have, or a property that these modular polynomials have, is that 2 elements in the upper half plane are related by a matrix with rational coefficients if and only if their J values are a 0 of a specific modular polynomial. Okay, so this statement here is the statement that this is the statement, whoops, what happened? Here. This statement is the statement that describes many of the important functional properties of the J function. It should be pointed out that this number n that arises like the index of the family of modular polynomials only depends on G and not on Z and W. So for specific G, the same n is going to work. So another way of saying this, a more perhaps geometric way of saying this, is that if you have a matrix with rational entries, well, then one thing you can do is you can define this polynomial here in 2 variables, m sub g. And this polynomial defines a plane curve in C squared. And this plane curve then has the property that if you apply J to every point of it, you will get another plane curve. Well, you have to restrict to the upper half plane, of course, but it has this property that if you take the plane curve, you restrict to the upper half plane, you apply J, you get another algebraic curve, which is given by the zero locus of a specific modular polynomial. So in this sense, the J function, although it's a transcendental map, will sometimes take an algebraic curve and give you another algebraic curve. And not just plane curves, but more generally, it can take certain kinds of varieties in C to the n, which are defined by Möbius transformations or by Möbius polynomials. And if you apply J to that, you will get another algebraic variety, this time cut out by modular polynomials. Okay, so these are certainly very important varieties when it comes to the properties of the J function, because the J function is somehow able to distinguish them as varieties besides every other kind of algebraic variety you can find. And so they have their a specific name associated to them, which is that they're special. All right, so a variety of the form we have just described, which is cut out by modular polynomials, this is called a special subvariety of C to D. And here there's a small example, which is like if you just take the identity matrix, okay, then the number n that corresponds to the identity matrix is 1, and it turns out that the first modular polynomial is x minus y. And of course, the zero locus of that is just the diagonal of C squared. And so this is saying that the diagonal is a special subvariety. Now, the special subvarieties have very good properties or have a very good behavior set theoretic-wise, in the sense that, for example, if you take two special varieties and you intersect them, then the intersection is again special. Or really, I should be saying that the reducible components of the intersection are again special. That's perhaps probably not so difficult to figure out, because if you intersect two of these things, well, you're just adding more modular polynomials. So of course, everything checks out. But in particular, sometimes you can intersect two curves and get points, right? So you can take two special curves, intersect them, and you get points. And those things are called special points. So in general, if you intersect one special curve with the diagonal, unless you already chose the diagonal, then that intersection should give you finitely many points. All right, and those points can be found by, for example, solving this polynomial, finding the roots of this polynomial now in one variable, phi n of xx. Or also, because of this equivalence between the Möbius action and modular polynomials, you can also try to go and find the fixed points of non-scalar matrices. Okay, and then apply J to those solutions, and those will be the corresponding special points. And they are special points in the sense that they are special subvarieties of dimension 0. Now, they have a very important modular interpretation. I mean, going back to the fact that the J function gives a modular structure to the complex plane, these are usually called singular moduli, the special points, because they correspond under the modular interpretation to complex elliptic curves that have complex multiplication. And there is a very classical theorem of Schneider that says that special points are those arise from those numbers in the upper half plane, which are bi-algebraic with respect to the J function. So they are algebraic. This is an algebraic number Z that stays algebraic after you apply J. This is an equivalence of statements. Okay, so this was just a little bit of background on the J function and its important properties. Mostly the fact that there are these special kinds of varieties which stay algebraic after you apply the J function. We understand more what are the defining equations of such things. And well, there are these particular special subvarieties dimension 0, which are called special points. All right, so in the abstract, what I said was I wanted to discuss 3 different conjectures that have different origins to them, but that interact quite nicely in certain situations. So I'm going to go through them now. The first one is a very famous conjecture these days in arithmetic geometry or in Diophantine geometry. It's called the Zilber-Pink conjecture, and it's at the center of a lot of research these days. So here's the thing. Suppose that you take some algebraic variety, then you might want to look at the intersection of your algebraic variety with all the other special subvarieties that are in C to the n, okay? And sometimes these intersections will have components which have dimension larger than expected. And if that happens, then you call such a thing an atypical component. So in other words, an atypical component of the variety V is something that arises from intersecting V with something special, T, and that component having a dimension larger than what is written here. The dimension of X must be strictly bigger than this expression on this other side. And that's simply because this means that then the dimension of X is larger than expected. So there must be, I guess the Zilber-Pink conjecture, we'll see now, is that what it's saying is that there must be a reason why, there should be a good reason why there would be atypical intersections with special subvarieties. So the Zilber-Pink conjecture is written here. It's not so long, as you can see. It says that any algebraic variety has only finitely many maximal atypical components. And maximal means under set theoretic inclusion. And so, like I said, this is a very important conjecture. It's an open conjecture, and it's at the center of a lot of research these days. And in particular, the Zilber-Pink conjecture implies the very famous conjecture of AndrÃ, which says that if a variety has a Zariski dense set of special points, then itself must already be special. That's the only way that a variety can have a Zariski dense set of special points. It has to be a special subvariety.
I don't. What exactly maximal on? What do you mean on?
It is not contained in like X is a maximally atypical component if it is not contained in a component of in a bigger component which is also atypical.
But I mean, we itself has a finitely many components, so I don't understand the announcement of the conjecture.
So for me, algebraic variety already means being irreducible. And so, but when you take a V and you intersect it with another algebraic variety, that intersection might not be irreducible. It might be, you know, it might have different components. So what I'm saying is X is a component of the intersection.
Okay. So because the number of the special varieties is infinite. Okay. Now I get it.
Yeah, exactly. So there are infinitely many special subvarieties.
Okay.
And so, yeah, so this is Zilber-Pink conjecture. It's very open. And as far, you know, there are a few things maybe very specific here and there, but the only thing about Zilber-Pink that has really been proven to a great extent is this AndrÄ conjecture. AndrÄ has a somewhat long history in Diophantine geometry, even up to very recently, because to some extent, the most general form of the AndrÄ conjecture was only proven last year by Pila, Anand Shankar, and Jacob Zimmerman. Okay, so this is the first conjecture that I want to talk about, the Zilber-Pink conjecture. It has its origins in Diophantine geometry. And well, it has to do with, it's saying something about the behavior of special subvarieties inside of C to the n. it's telling you something very special about like how they're placed inside of C to the special subvarieties. So we will talk more about this, and we will also talk a little bit about what is known. But now I want to go into the second conjecture called modular Schanuel. So modular Schanuel is a modular version of Schanuel's conjecture. Schanuel's conjecture is a conjecture for the exponential function. And this comes from the world, this conjecture here comes from the world of the study of periods. So this is the conjecture that arises from the period conjecture of Grothendieck-AndrÄ. I will talk a little bit more about this soon. So the statement first. Suppose that you have some algebraic variety, this time inside of Cn cross Cn. Because what I want to do now is I want to intersect V with the graph of the J function. That's what I'm looking at now, this Cartesian product. Suppose you have an algebraic variety in this space defined over the algebraic numbers, and that the dimension is strictly smaller than n. So then the modular Schanuel conjecture will tell you that if the variety has a point in the graph of the J function, then this point must lie inside of a special subvariety. Instead of a proper special subvariety. Yeah. So there must be some kind of modular relations between the J numbers, or if you want, there must be rational Möbius relations between the Z's. There has to be something like this. That's what the conjecture is saying. There has to be something like that. That's the only way that a point can be inside of a variety of dimension less than n. So that's the conjecture. And so I have a little bit of the history of this problem. Some of you might have attended last year, I think there was a talk in this very seminar from Christiana Bertolin, who spoke about, well, among other things, she spoke about her work on the period conjecture. And in the talk that she gave, she showed that Schanuel's original conjecture for complex exponentiation is nothing more than a special case of the period conjecture of Grothendieck-AndrÄ. That's the result that she presented. Well, and also other things as well. But in the same paper where Bertolin proves this, she also proves another conjecture, this time about elliptic curves. That's called the modular conjecture. And using this modular conjecture and working with the modular interpretation of the J function, you can get the result that I've stated up here. So this conjecture, this modular Schanuel conjecture, is also a special case of the Grothendieck-AndrÄ period conjecture. Now, the way that I've stated it here is not the way that it's most commonly stated, but the reason why I did this is because I want all of the problems that I'm going to present to you, all three of them, because I want them to play along with each other, I wanted to state them in a common language, in the language of algebraic varieties. So that's why I'm stating it in this fashion. But it is true that if you search the literature for this, you might find it stated in different terms. But it's equivalent. Okay, so this is modular Schanuel. Again, this is a very open conjecture, just like Schanuel's conjecture. Very little is known about this. And unlike Zilber-Pink, which is also very much open, this conjecture is not so much at the center of a lot of research because I think people don't generally have a strategy for this one. Whereas in the Zilber-Pink case, there's at least some point counting strategies that, well, they work for the AndrÄ conjecture. So people think that maybe if you push them harder, you might be able to get some partial results about Zilber-Pink. But here it seems to me that the general consensus is that there's not a very clear strategy for this problem. Still, it doesn't mean that there's nothing known. We will see that there are some things about this. Okay, so this was the second problem. And now I want to come into the last one, which is existential closeness. So existential closedness is a conjecture that comes from the world of model theory. So model theory is a branch of mathematical logic. And the name of this conjecture should reveal something about what it's trying to do. Technically speaking, what happens is that in model theory, it would be a very good thing to know if your models are what is called existentially closed. Existentially closed means that if you have a logical formula with such as existential quantifiers, then you can eliminate the existential quantifiers. That's what it means. In the world of algebraic geometry, for example, if you just talk about algebraic geometry, then existential closedness in that setting is known because it amounts to proving Nullstellen sets. So in some sense, existential closedness can be thought of as a form of Nullstellen sets for, in this case, more general forms of equations, not just polynomial equations. Okay. So once again, I'm going to intersect an algebraic variety with the graph of the J function. So I have to work in the product space. Now, a variety is going to be called free if it is not contained in something special, in something that the J function thinks is special, which is to say, the variety is not contained in any variety of either of these two forms that I've written down here. Something medius with rational coefficients, or something's proper special, all right? So that's what you call free. The variety satisfies no, it's not properly contained, it's not contained in anything that would be considered special by the J function, except for the whole space. Now, a little bit of notation. If you choose some numbers between 1 and n, some indices, then you can always consider a projection that goes from Cn to Cn into the smaller set of coordinates, where you just project the first n tuple, you project it to those coordinates you've chosen, and you do the same thing with the second n tuple. You just preserve the indices in I. That's what you're doing. So this is all that's happening. This is just a little bit of notation to make some statements a bit easier later on. Now, a variety is going to be called broad if, under any such projection that I've just described, the dimension of the image is at least half the dimension of the ambient space, is at least L. Okay, so in particular, if you take the tuple I to be all the numbers between 1 and n, that means that the variety itself has dimension at least n. Okay, so that's what we call a broad variety. So now I can, well, this is another piece of notation. This is E sub j to the n. This is the graph of the J function in n variables. And now I come to the existential closedness conjecture. If the variety is free and broad, then the intersection with the graph of the J function should be Zariski density. That's existential closedness. So why this free and broad? What's going on? Well, freeness, what is freeness doing here? Freeness is there to ensure that you're not breaking, that the variety V is not breaking any of the functional properties of the J function. If you don't ask for V to be free, it's really easy to come up with examples where the intersection with the graph is empty. So, for instance, one thing that can go wrong is that the J function is not defined over the real numbers. So if you, for example, decide to set some of the first n coordinates to be a constant real number, there's no way that this variety can possibly have elements in the graph of the J function, because freeness also requires that you have no constant coordinates. So freeness is there to just ensure that you're not going to break trivially any of the functional properties of the J function. And then broadness is there just to ensure that there's enough space for the variety to have points in the graph of the J function. Because, I mean, if you believe modular Schanuel, then you know that if the variety is too small, as the dimension of the variety is too small, then having points in the graph of the J function could only happen if the variety V intersects a special subvariety. And so this is perhaps too many restrictions on V to even believe that there could be points in the graph of the J function. So that's why freeness and broadness are stated here in the conjecture. And it is believed that this is enough to ensure that there's going to be a Zariski dense set of points in the intersection. So not just one, but actually a lot of them. Okay, so these are the three conjectures that I wanted to talk about today. These are three conjectures from the three different worlds, points of view. And hopefully it is not too difficult to believe that there are versions of all of these conjectures for any of the other functions that you might, consider. Like if you consider the exponential function, or if you consider the Weierstrass P, or some automorphic function, there are versions of these things for all of them. So now what I want to do is I want to show you a circumstance in which these conjectures all come together and play with each other very nicely. And this is the part which explains the title of the talk today. Okay, so generic solutions. Let's assume that these three conjectures all are true, all right? So what do they tell you about each other? Take a variety inside of, again, the Cartesian product space, which is free and broad, defined over the algebraic numbers, and assume that it has dimension exactly equal to n. So now the question that you can ask is there a point in V, which is also in the graph of the J function, which is generic in V? So generic in V, what I mean is that the transcendence degree of the point equals the dimension of V. Okay, so well, let's see. By existential closedness, because the variety is free and broad, you know that the intersection with the graph must be Zariski dense. Excellent. Now, suppose that you take one point in the intersection and this point is not generic. That means that the transcendence degree of the point must be strictly less than the dimension of V, and the dimension of V was n. Now, by modular Schanuel, if the transcendence degree of the point is strictly less than n, that means that this point lies in a proper subvariety of V, also defined over Q or over Q bar. So by modular Schanuel, you will be able to find a proper special variety that contains J of Z. And because of the equivalence between the modular polynomials and Möbius transformations, you can find a corresponding Möbius variety defined over Q that gives you T as image. That's just by definition of the special varieties. So at this point, Z, J of Z must also be inside of the Cartesian product between M and T. Now, there might be more than one T that has this property. There might be more than one special variety that contains J of Z, but among all of them, choose one where the dimension is minimum. And choose the corresponding M for that. Okay, so now comes Zilber-Pink into this picture. You say the point Z, J of Z is now on one hand inside of V, and on the other hand is also inside of M times T. So it must be in the intersection. And so consider an irreducible component of the intersection that contains this point, X. Now the intersection between V and M times T, I'm going to rewrite it in this other more convenient way that is here at the end. Well, because it will make some calculations a bit easier. But it should be clear that this is an equality. I mean, there's nothing deep happening there. So if I'm going to try to use Zilber-Pink, I need to find something atypical. I need to find an atypical intersection. So X is my candidate, and so I would like to find the lower bound for the dimension of X. Okay, so the dimension of X is at least the transcendence degree of any of its points. All right. So in particular, this point Z, J of Z. Now, using modular Schanuel, you can actually say that this point will have transcendence degree at least the dimension of the special variety T. But on the other hand, if you wanted to check that something is atypical, you would have to look at this combination of dimensions here. The dimension of the variety, the dimension of the special variety, and then the dimension of the ambient space. And combine them in this way. So, okay, you do that. Now, the first thing that you can observe is that the dimension of V intersected with M times C to the N must be strictly smaller than the dimension of V, because V is free. So that is why you get a strict inequality here. On the other hand, everything else, is just what it is. Nothing else has happened in this expression. The dimension of C to the N times T is just the sum of the dimensions, and so I added them together, I got this. Now, the dimension of V was assumed to be equal to N, so you get that this is less than T, equal to T, the dimension of T, and this is at most the dimension of X. Sorry, this here should be no. Okay, oh well, this should be, instead of X, you should say the dimension of X there. Okay, so yeah, the whole point of this was to try to use Zilber-Pink. Now, in order to use Zilber-Pink, what you can do is you can project this whole picture onto the second factor, okay, onto the second version of C to the N. And if you do all the counting of dimensions correctly, you will observe then that the projection of X gives you an atypical component of the projection of V. And so Zilber-Pink says that the projection of V can only have finitely many maximal atypical components. Now, V is free, so those atypical components must be proper subvarieties of V, or of the projection of V. And because there's finitely many of them, and they're properly contained in V, and the intersection with the graph was assumed to be Zariski dense, you can just go and find another point that avoids all of these atypical components, and that will have to be now generic in V. Because essentially what we showed was that not being generic in V amounted to there being the explanation why a point is not generic in V is because it must be contained in something special. And those special things can only arise in finitely many ways, essentially. Okay, so this is what I wanted to, this is what I meant when I say the three conjectures all come together in a very nice and natural way to produce something like this, talk about the existence of generic points in varieties. And so I've summed it up in this way. If you assume all three conjectures, then you get the existence of generic solutions. Which, okay, is fine. It's a really cute combination of inequalities to play around with, but I don't know, it might not seem like particularly meaningful at this point because everything that I've said so far is conjecture. So maybe, it might be satisfying like in a formal point of view, but it's not super, perhaps, illuminating. So I would like to talk about certain things now, certain things that are definitely true. Okay, so like I said, these three conjectures all of them are open, but that doesn't mean that we don't know anything. So now I want to discuss a little bit about what we know in each case. So the first thing is, in order to be able to talk about these things properly, I need to talk about weakly special subvarieties. So this is just a small change from the definition of special variety. As you remember, special varieties were defined by modular polynomials. So the only difference now is that aside from allowing modular polynomials, you also allow setting some coordinates to be constants, any constants you want. Okay, that's the only difference between weakly special and special. So here is something we do know, a very, very important theorem. This is the X-channel theorem for the J function, proven by Pila and Zilber-Pink in 2016. And what it talks about is about the dimension of the intersection of a variety with the graph of the J function. So suppose you take an algebraic variety, again in the Cartesian space, and then you look at a component of the intersection of V with the graph of the J function. Then you expect the dimension of the component to be this specific number here, the dimension of V minus n. Unless, if this doesn't happen, there must be a good reason for this. And the reason is that the projection of U onto the second factor must be contained in some proper weakly special subvariety of C to the n. Okay, so this is the X-channel theorem for the J function. And I guess that the way that I've set everything up, it should not be so difficult to believe that this is going to tell us a few things about the problems we've discussed already. Now, I think that whenever I present this theorem, I sometimes feel the necessity of explaining a little bit of the name of the theorem, because it's a theorem named after two people, but it's proven by neither of them. So you might be wondering why X and Schanuel are there if this is a theorem of Pila and Zilber-Pink. Okay, so just briefly, the way that the story goes is that, as I mentioned earlier, there's this conjecture of Schanuel about the exponential function, which came up in the 60s. I think the first time that it was printed is in a book of Lang on his Introduction to Transcendental Numbers or something like this, or Transcendental Number Theory, it's called. And there he states the conjecture of Schanuel. So this came out in the 60s. Now, in the early 70s, 1970 even maybe, James X gave a proof of, not of Schanuel's conjecture, of course, but something close to this, which is that if instead of looking at Schanuel's conjecture over the complex numbers, you look at the conjecture over the field of power series, where you do have an exponential again, then the transcendence, the conjecture of Schanuel does hold on the field of power series. And so this is a theorem of X about Schanuel's conjecture. And well, eventually that became known as the X-Schanuel theorem. And because of that, then every other theorem that sort of like gives you the same kind of statement about a specific function has been known as the X-Schanuel for blah, that particular function. And yeah, recently there's been like many of these X-Schanuel theorems have been proven. We now have X-Schanuel theorems sort of like for all of the circumstances that I mentioned earlier, like all of the exponential functions, all of the automorphic functions, Shimura varieties, variations of Hodge structures, they all have a particular X-Schanuel theorem for. So yeah, I mean, all these games we're going to play later from this point onwards should be you should be able to replicate them in all of these other circumstances. Okay, so how do we use X-Schanuel for the problems that we care about that we were just talking? Okay, so let's talk about Zilber-Pink first. So Pila and Zilberman, already in the paper that they wrote about where they proved this theorem, they showed that the X-Schanuel theorem gives you a weak form of the Zilber-Pink conjecture. So how, in what sense is this statement weak? Well, so I need to alter the definition of a typical component slightly to get this thing called strongly atypical components. What is a strongly atypical component? It's an atypical component with no constant coordinates. So you can see that there is something happening already at the level of what kind of things X-Schanuel can tell you, because on one hand, X-Schanuel speaks about weakly special subvarieties, no? And the definition of weakly special differs from the definition of special only in that it allows some coordinates to be constant. And now Zilber-Pink, or the weak Zilber-Pink, is going to talk about strongly atypical components where you do not allow coordinates to be constant. Okay, so this is actually part of a very general phenomenon that in order to understand Zilber-Pink, it seems like the hardest problem is everything that has to do with constant coordinates. If things have constant coordinates, then it's really like extremely harder, as it turns out. But well, let's see what we get. So the theorem, so Peel and Zimmerman, like I said, showed in the same paper as before that you get this thing. You don't get exactly Zilber-Pink, but you do get that every variety has only finitely many maximal strongly atypical components. So as long as you only allow atypical components with no constant coordinates, then you do have the statement. Okay, that's good. It's not the full Zilber-Pink, but that's a start. You know, something to work with. Despite it not being the full Zilber-Pink, there is something to be said about intersections where you do have constant coordinates. So this is a result of
Sebastian, maybe this constant that you are telling, and also the field of definition of V, it's not clear. It can be just any complex number. Or
oh yeah. So there's no restrictions here on the definition, on the field of definition of the variety so far.
Okay.
Yeah. It's only the other conjectures that I mentioned that sometimes they have restrictions on the field of definition. But these are, these statements at least have no restrictions. They work all the time. So yes. So here is a result of Aslanian of 2021, where he shows that, okay, you don't get the full Zilber-Pink, but you do get something a bit close, you know, sort of like as good as you could possibly make it with the material that we have so far, which is that you don't get finiteness of the components, but you get finiteness of something else. So suppose that you have an algebraic variety and that it has an atypical component X, which comes from the intersection with something weakly special T. Then you can find perhaps another special variety or another weakly special variety T0, but this time so that the indices of the modular polynomials defining T0 is bounded. And this bound depends only on the variety V. So this is what I mean when I say you get another kind of finiteness. You don't get finiteness of X, of the components of X, but you do get finiteness on sort of like what is called the complexity of the weakly special variety, which is the maximum of the indices of the modular polynomials. So you know that's all right. That's good. It gives you something that you can say now about atypical components more generally. And it really, in a very precise way, reduces this whole situation to saying like, okay, yes, it is actually true that the whole problem with Zilber-Pink is this constant coordinates thing. To some extent, the modular polynomials are sort of taken care of because there's this finiteness on the index. Cool. So what happens if we try to use now this weak Zilber-Pink in the previous argument that we discussed earlier? So earlier we were saying like, okay, you know, if you happen to have a point in V, which is in the graph of the J function, but it's not generic, then that point produces an atypical component. So this is still true, but if you wanted to use these results that I've mentioned here, which are known, then you cannot use the full Zilber-Pink. You have to use these weak versions. And the problem, of course, is what do you do with the constant coordinates? So what happens, as it turns out, is that the constant coordinates that are going to show up that might give you problems because of modular Schanuel will be special points. So the constant coordinates that show up in the issues that we've discussed will be special points, as it turns out. And so, on one hand, you have the weak Zilber-Pink, or the proposition of Aslanian that I've just mentioned, that takes care sort of like of the modular polynomials that can arise. And then on the other hand, there's the AndrÄ result for products of modular curves proven by Jonathan Pila in 2011, which takes care of the special points. So combining these two results in a convenient way, you can actually make do with only known things and get rid of the conjectural part of Zilber-Pink. So this is something that we worked out with Sebastian Herrero. Well, we're still working on it, so it's not available yet. That's why I'm not exactly sure, but hopefully not too far from now, in a couple of months, you will find this on the archive. You don't need Zilber-Pink to get the result we mentioned earlier. Modular Schanuel and existential closedness are actually enough to get generic solutions. Okay, so excellent. That is one very good thing about Schanuel that allows you to work with. But what about the other conjectures? What about modular Schanuel and existential closedness? So, modular Schanuel first. As it turns out, Schanuel, of course, has something to do with Schanuel's conjecture, and in a very concrete way, as it turns out. So, I've written it here, like, morally speaking, what Schanuel says is that modular Schanuel is true in general. And so what that means is this. This is a result that I showed some years ago, essentially saying that there is a specific countable subfield of the complex numbers where any problems with modular Schanuel will show up. But if you work outside of this field, modular Schanuel is true. Okay? So that's what I mean when I say modular Schanuel holds modulo Cj. As long as the point that you're considering is not in Cj, modular Schanuel will be true.
So this is a kind of a list of some finite values of J function, or?
No, it's a countable list of values.
Okay.
Yeah.
But these are not in the values in the upper half plane, rather the image of the J.
Well, so it turns out that you can look at it both ways, because this field Cj happens to be closed under the action, under taking the J function. So a point is in the J in Cj if and only if the preimage is in Cj. So either of them, either you look at Z or J of Z, they will be both in Cj, or none of them will be in Cj. Yeah. So in some sense, what this means essentially is that modular Schanuel has at most countably many counterexamples, if it has any, and they are found in this field Cj. Yeah. Okay, so this is something also again to work with. So for example, if we decided to take a variety V at this time, choose it so that it's not definable over Cj, then because of Zariski density with the intersection with the graph of the J function, you should find points in the graph of the J function in V such that the coordinates are not in Cj. This is just like a standard like Galois theoretic consideration, because it turns out that the Cj is algebraically closed. Yeah. So one thing that we could try to do now is play with the field of definition of the variety V, so that you are outside of Cj, and then we can get modular Schanuel to work. Okay, so now existential closedness. So these first two things that we talked about, Zilber-Pink and modular Schanuel, both of them we can get some partial results using Schanuel. When it comes to existential closedness, you don't need Schanuel, at least not for the statement that I'm going to give. So with Sebastian Herrero, we already showed that there are certain kinds of varieties for which it is known that existential closedness holds. Specifically, if you have a variety, and this time you project to the first factor, okay? You project to the first factor and you get a dominant projection, meaning that the dimension of the projection of V is n. If that's the case, then the intersection between V and the graph of the J function is seriously dense in V. So V does satisfy existential closeness. This is not restricted to Schanuel, this theorem. This theorem works with like more, standard, I guess, methods. You have to use complex analysis, and you have to do, like the study of modular functions and so on. But through some work, you can produce this, find these solutions, these points in this intersection, and lots of them, in fact. So, like if you wanted to combine everything now that we've seen so far, you combine all of the things together, all of the known results, we are able to, in fact, produce something completely unconditional. So to take a variety inside of Cn times Cn, which is broad. Now, the first thing that I'm going to do is I'm going to restrict the field of definition of V so that I can apply this version of modular Schanuel that we know is true. And this is what this definition here is doing. Having no Cj factors means, to some extent, that V itself is not definable over Cj, and also that the projections of V, in the projections in this sense, are either very large, or they're also not definable over Cj. All that this definition is doing here is allowing me to use the known results about modular Schanuel. So again, with Herrero, we worked things out, and we showed that, okay, suppose then you assume all of those, you take a variety which is free, is broad, it has no Cj factors, and the projection on the first part is dominant. Then you can use all of the known results, and you do get generic solutions of V inside of V, completely unconditionally this time. So although the original argument that I gave was, completely conjectural, it does give you a strategy once you have like some ground to stand on, even though you don't have the full conjectures, there's still enough material to work with there to produce something like this. Yeah, I think my time is up, so I think I'm going to stop here. Thank you very much.
Okay, Roberto. Sorry, Roberto. Okay. I have many questions. Maybe stop recording and then I will ask.